is actually using extron scalar. I think it's actually using some other device for the sound. Let's go to the microphone. Okay. That should be better. Testing. Okay.
Yeah, guys.
Which one do you?
If you have a look, I mean, I don't. So it was actually on X. Which I don't even know what that is.
Maybe that's this one.
So I switched it to Samsung Go mic.
Oh yeah, no, that's yeah.
So let's hope that works. Yeah.
Extron scalar D.
So this is a ViewSonic. So. I mean, we have proper mics here.
Yeah, but they are. I don't know if they are. Maybe because you're on Bluetooth, it's possible.
Maybe that's what the Extron is. So that's a Sennheiser. Okay. Doesn't really matter, I guess.
The question is whether that will feed through the. It's the.
Well, that's it.
It's the folks online that.
I know. But presumably this is connected via USB.
It comes
To that
behind you.
It's not connected to the computers.
I don't know if
It's actually, are you saying it's actually, you can hear it coming up?
yeah.
Yes, then we should switch that off. Oh, that's what we on.
Extra volume. No.
Extra volume. I really need it. Yeah, it says Extron here.
So I think it's still a good option to use.
I think maybe the Extron is the one to use, you know. Let's go for that because that was offered here as an option. Let's see. So.
Oh yeah, but it's probably Bluetooth.
It's
called the Extron. It's not the extra.
If you use the extra, then you're not using this. That's correct, which is better because you heard when you were talking earlier. I was on it.
Maybe ask with the audience.
Yeah.
Maybe step away from all these. Okay, maybe go with the microphone over there.
Is it coming up? Really? Must go through. I mean, like this way.
Good way of turning up the Extron scalar D.
Maybe the Extron is just somebody's noise canceling headphone.
No, but it says Extron on the machine. Oh yeah, no, I think I have one. We don't. Yeah, that's what I was thinking of.
So 16 years. We've been running continuously here. We've only had 1 year not in person. Only 1 year. What year was that? Okay, well, let us make a start so that we all press and move on out a bit more time. I want to welcome you for the first time against my facility, and those of you who have come here before, welcome back. This program we've been running here in London for actually 16 and it was actually run continuously right through the pandemic when gets mad in all the cities online. So we held it 1 year partially in Skype, and another year we held it both in Paris and in London, and it's continually evolving. It's only possible thanks to the hard work of the folks in the consortium, many others, another and also from the funding system we've gotten over the years. Initially it was from the partnership, the funding. I am, in fact, many people come here from the US sell them, don't know how in default, but we're spending the cost. So the thing about this meeting is that we have lots of discussion. We particularly encourage questions from younger members of the community. The most important thing you learn in this is how to ask a dumb question. Sometimes it's going to have a dumb question. So you just got to keep asking. Even if you're sitting right at the back of this room, things aren't questions. And that means that when we have an 18-minute slot for a talk, really only means 50 minutes of the actual presentation, and half an hour or more for questions. Yeah, we're still getting proud of that. We have usually have immediate get. There's one very small bathroom just around here. Get down, get some more coffee. Room in which we're going to have this meeting change today, we weren't able to get one room. Oh, only 1 day. That's good. We have a public lecture on Wednesday evening at the you're cordially invited to come, although questions James says the talk will involve no equations, main anecdotes, and as regards quantum mechanics, no one else does anyway, so so please invite your friends. There are and going to have a poster evening tomorrow from 6 to 8 o'clock. That's in the Senate House of the University of London, and directions that are online. So basically, we're going to be wine the poster give further instructions and the informality of this event is quite a fact. We have chairs by the open up chairs morning, and I'm really happy to welcome Malte Grosche. Today is a day with a lot of focus on the unconventional superconductors. The determined superconductors. I've got 2 talks this morning on this subject. Welcome, Malte come down.
Thank you. Thank you very much. I can maybe use a minute to get set up here. So understand the microphone is necessary so that people online can also hear me. There may not be anybody on, but can you hear me? Okay. Okay. So thank you very much, Peter, for this kind introduction. Because I've never made it before. And the reason for that is largely that we have exactly what the question I want to address.
They're not hearing very well.
Is that better? Or is it the microphone itself?
I think very little. Just mumbling.
Well, that's just my normal. That's what my No, but the other one has the same microphone. It does what it's supposed to do, right? I mean, we can hear all the cracking sound.
But it's really a question of the computer.
So you can certainly hear me, but the computer can't receive. Maybe shall I just go on the iPad phone then? The microphone, that might actually be simple. Okay.
So maybe don't use this accent.
Yeah. I've just switched that off.
Now it's fine.
All right. Okay. Okay, is that better? Can they hear me now? Which is basically the iPad. I'm on the iPad. Okay, right.
No, I'm good. Yes, sir, it's clear now.
Okay.
There you go. That's good.
Okay. So so Piers mentioned that the talk will introduce uranium tellurium-2, and in fact, that was of course the intention with the initial talk, which would have been given by J.P. Fagnoni.
He's going to speak this afternoon.
But that's been swapped, so he's speaking this afternoon. And I'll also mention UTe2 if I get to it, but that depends on how many questions you ask on the way there, because I have a broader spectrum. The main question which I'm interested in is, how do we find new unconventional superconductors? And which is perhaps a little broader, but of course, UTe2 is one of the most exciting recent findings, and we'll get to it towards the end of the talk. And in particular, there is an aspect of heavy fermion superconductors I find intriguing, namely that many of them exhibit very high upper critical fields. Like this one, CeSb, which is the ultimate topic of the talk we found in Cambridge a few years ago, also has upper critical fields which appear to be too high. So, but on the way, I want to go through a number of areas which aren't fully developed and understood in my mind, but I thought for this kind of school or workshop, might be interesting to bring them up. So hopefully you can think about it. And the first one is this observation that if you have propagating modes, undamped propagating modes, okay, they tend to have of course, their spectral weight will be at the resonance frequency. But if you damp them, by the damping shifts spectral weight to lower frequency, makes them more relevant at low temperatures. And in particular, if they become overdamped, this is perhaps obvious to anybody working on the theoretical side, but it wasn't so obvious to me until I actually saw it. If they are overdamped, it dramatically shifts spectral weight to low frequencies, and they become, in some sense, more relevant. Next topic is the origin of mass renormalization in interacting systems. And what I'm going to show, basically in two experimental studies, is that largely the mass renormalization we can understand as arising from local interactions. Whereas long-range interactions, which are going to be important near quantum critical points, may be more relevant to superconductivity and also non-Fermi liquid power law exponents in transport. And then finally, heavy fermion superconductors which exceed the Pauli limiting field. So first of all, a bit of motivation why superconductivity, I think, has a renaissance, it's resurgent, and large part of the motivation for me comes from the dramatic development of demand, large volume demand for high-performing superconductors, much of which is driven by commercial fusion research. So again, perhaps you all know this, but for me, this was a bit of a revelation a few years ago when I realized that there's a real industry growing in that area. We don't know whether commercial fusion will become a reality over the next 10 years. The companies involved in it think it will. They're basically talking about the first commercial fusion reactors in the early 2030s. But that's always a little bit beside the point. The fact is that they're building research reactors and they're getting a lot of money for it. So there are various commercial companies now building fusion research reactors. It's a big one in the United States, Commonwealth Fusion Systems. Yeah, they've got billions of, they've got, I think, $2 billion venture capital. There's a substantial one in the UK, Atomic Energy. I recently saw that two former PhD students from the Cambridge Low Temperature Physics group work there now. So, and both of these companies, and there's a third one in New Zealand, as far as I know, both of these companies exploit the fact that if you use cuprate-based magnets, you can operate at much higher fields. And they call them 2020 magnets, 20 Tesla at 20 Kelvin. So you can operate at much higher fields than with conventional superconductors. And that, obviously, that shrinks dramatically the size in which you can confine the plasma. Shrinks the volume, plasma confinement volume, by a factor of 50. Right? So this shows sort of the size of the facility as a function of field. It's literally just a matter of working through cyclotron problems, like Lorentz force equal centrifugal force. And if you can shrink the size of the plasma by a factor of 50, and the volume comes down, you know, what used to be like the multinational conglomerate like ITER, which I've seen recently because I was in the vicinity. I wasn't inside, but I saw, like, it's a huge building basically, you know. And here you can, this is actually a person inside the reactor for scale, right? So you can basically make a fusion reactor in a room, right? So now it becomes something that companies can become involved in, and they do. Because if it's successful, they'll make a lot of money. Right? And so they're given money. And now they need the superconducting tape to build these reactors. And they need thousands of kilometers of superconducting tape. It's actually quite hard to make this tape, because it has to be almost single crystalline over the entire length. Right? So there's a whole bit of engineering and material science. How do I make high quality, you know, superconducting tape? And in the like, let's say 2010, 2015, they could make a few kilometers. But to make such a reactor, you need 1,000 kilometers. So what happened was that over the last 7 years, the production ability of a global volume has gone up by a factor of 10. Price per kilometer has gone down by a factor of 10. And that only just sort of produces per year, right, enough tape to equip one of these research reactors. So now what they're saying, well, if this works out, we want to make actual reactors, which will be bigger, and we won't just have one; we'll have hundreds. Right? So there's actually an industry growing of companies which are making superconducting tapes, and ultimately the volumes they're talking about, in terms of area that has to be deposited using pulse laser deposition, is similar to the TV flat screen production volume globally. Right? And so there's a lot of growth potential there. So, and that's just using superconductors. So,
can you explain once you have the high fields? I'm having trouble connecting the dots between having these really high fields and what happens. Like usually, the fusion is a huge plasma physics lab or something like that. So we have the high fields. How do we get the high fields?
I guess it's company secret, right? No, but of course that's all.
No, it's not hydrogen, it's typically tritium, and it's really complicated. And there isn't enough tritium on the planet to even do 100 of what they want to do. But I will say, can I plug the magnet lamp? So we're the highest buyers of HTS coated conductor tape, and all of a sudden we noticed a few years ago that we're not the biggest, buyers. And the fusion companies are thanking us because we've been going back and forth with the materials microanalysis to make the tapes better. So we're going to be using that a lot in our proposal, how we help the nation. Okay.
So I think it's an interesting question about the tritium, and I was also wondering about this. And apparently, what they intend to do is they want to breed the tritium in the reactor. Right? So it's basically tricky. Right? There is, like you said, there isn't enough. There are like about 26 grams in the world or something, and which you can use for the occasional test. And then they want to basically transmute, I think maybe lithium, into tritium in the reactor. And obviously, that's an important step to sort out for them. Right?
Look what Jeremy did with reactors. So maybe there's hope.
Anyway, I hope you don't probe me much further on how fusion works in detail. Because the point I'm trying to make is, like, it took
the online folks say, can you repeat the questions because we can't hear them so well.
Thank you. Right. So yeah, the question was, how does fusion work? And, but ultimately, whether you do it in ITER at like a few Tesla, or you do it in one of these reactors at, I guess, maybe 14 Tesla or 12 Tesla, it's the same principle. It's just that you can shrink the facility, so it's cheaper to do the experimentation, and then presumably they'll scale it up again when they actually run the main.
I do want to make. Let me repeat this. The one thing that Laura didn't say is that
is that there was a key innovation that took place in the last 10 years. And that was to rip off all the insulation from the tape. And that means that they're now stable against quenching, whereas with the insulation, they were not stable against quenching.
True.
So this was a huge.
I mean, I suspect it's basically like, I don't know, rocket technology or any other major technology. You know, there are many, many things that you have to sort out, and the insulation is a nice one. The what they're saying is you can hit this magnet with a hammer while it's at 20 Tesla, and it won't quench. Like they're so stable. No, you don't think so? Well, they have tried it. So, anyway, so but it also means, you know, the fundamental science discovery, which happened in the mid-1980s of cuprate superconductors, took 40 years to turn into a major application into an industry. So there can be a long delay, right? And the question is now, so that basically makes a step change. We've been working with niobium-based superconductors, which were discovered in the 60s, but they're still the mainstay for MRI scanners. Right? Half the world's MRI scanner magnets are made here in England, in Oxfordshire. But the next step are these cuprates. But it took 40 years to master all the challenges and so on. The question is, what will be the material platform 40 years from now? So, you know, we won't want to work with cuprates forever, so we need to go to the next materials. And so how do we find new systems? And, you know, it's really, I think it's maybe the most exciting period for me. I've been working on superconductors since I was a PhD student, and there have been material breakthroughs with the hydrides in particular, superconducting hydrides, which are really exciting in terms of their transition temperatures. We have real, like, actual real-world applications. We don't just dream about them. I mean, like, they actually there's the demand for getting the superconductors in tons, thousands of tons annual per year production. They are very interesting fundamental ideas. There have been fundamental breakthroughs and findings, like I highlight here CeSb and UTe2, and also UTe2. And to make progress, I think, it's important not just to look at the materials we already know, because it's difficult to give a talk about materials I don't know. So I will talk about materials we know. But my thinking is always motivated by the question, how can we turn this around to find the next one, to find new unconventional superconductors? Because with every new one we find, okay, we can fine-tune our understanding and get more clues about how to find other ones in a more directed fashion, which can actually have functional applications. Okay, and so the principle that has been quite successfully applied at Cambridge, and of course many other places, is to look at the threshold of magnetic order. A generic example here was serine plating to silicon 2, where as you tune away magnetism as a function of pressure, a small bubble of superconductivity appears tagged on to the border of magnetism. Right. So we think, okay, looks like it's not that magnetism removed or screened away superconductivity, which would otherwise have been all over the place. No, the superconductivity actually only lives on the threshold of magnetism, where, of course, you would expect strong magnetic fluctuations. So presumably this has something to do with the magnetic fluctuations. Maybe the pairing interaction that binds the superconducting Cooper pairs is magnetic in origin. And another important one was uranium germanium 2. Andrew is here. Can you visualize it? So where the superconductivity even appears within the ferromagnetically ordered state, but close to the border of it. And maybe there are relevant links with the case of uranium tellurium 2, another really interesting uranium-based superconductor. And basically, just following this guiding principle, searching around interesting materials, we found a whole lot of new superconductors in Cambridge, largely inspired, of course, by Gil Lonzerich, who really was a big proponent of this idea and inculcated the whole group, and maybe many other people, you know, with the idea that this is a good principle, good guiding principle. The problem with the principle is it isn't actually quantitative. So I brought up here the famous Matthias rules, right? So Bernd Matthias found a lot of conventional superconductors, hundreds, and he formulated some guiding principles. And maybe there can be similar guiding principles for finding unconventional superconductors. But I think the most important one, we should really be at this step. So rather than just saying, okay, we want to be near the threshold of magnetism, what I'd like to see is real computational filters where I can throw in long lists of candidate materials and they'll say, well, these are the likeliest candidates. So it would be nice to take it to the next step where it's not quite so heuristic. Basically. So I would like to have a more practical understanding, which can lead us towards discovery. And we know that this is possible because the superhydrides work was largely done that way. Because if you're looking for new superconductors at millions of atmospheres, you can't do high throughput screening. You have to have a fairly good idea what you should try. So there was a very strong interaction between computational modeling and experiment in that field. Of course, it's easier because they're conventional superconductors. So you have a very good, very advanced mature theory to use. It's much harder to do in our field. Okay, so the first material class I want to introduce is basically there to illustrate the importance of low energy modes. In this case, they are just phonons, lattice vibrations. So this is work which goes back a few years. It was initiated by Sui Go, who's now a professor in Hong Kong. And as usual, there are a whole lot of PhD students and postdocs over the years involved with this. Should also mention Bartomeo Montserrat at the Material Science Department in Cambridge, who's running quite a strong, very active computational materials group there now. And he and his student at the time, Ken Akala, did phonon calculations on these materials. So the basic idea is we're looking for materials, it doesn't matter if they look complex, materials which have a structural transition that can be tuned to zero. And in this case, in this material class here, the mica phasors, 3, 4, 13 compounds, which by the way are also superconducting at low temperatures, that structural transition is second order. So it's a continuous phase transition. And what we found was that by either chemical pressure, i.e. replacing some of the strontium here by smaller calcium isoelectronic substitution, or by applying pressure, hydrostatic pressure, you can suppress that structural transition gradually until it really goes away. So now you have effectively a structural critical point, if you will. So, and the striking thing is, of course, it was motivated by the idea of maybe something interesting happens to the superconducting transition, and it is interesting, but it's not super interesting. TC goes up a little bit. But what was really surprising was that the resistivity becomes linear in temperature down to TC. You can think about it like that. It's a kind of question of nomenclature. You know, some people call it charge density waves, and then other people say, but it's not strictly charge density wave. You could attribute it to some nesting features in the Fermi surface, but whether it's a fully cubic 3D material, whether that would have been enough without some other instability, you know, to induce this changes question.
What is it reading?
What?
What is it reading?
Yes, so nothing there. So the initial, our collaborators in China, I'm afraid, was it Yang? Anyway, I can't remember the group who sent us the initial samples. They thought that this was, in fact, the spin density wave transition. But we became more and more convinced it's not. It's actually just structural. One aspect was there's like a slight decrease in the, like you can see the magnetic susceptibility is more keen that it decreased, and was just plausibly explained by the reduction in the density of states, which happens when you gap out part of the Fermi surface as part of this increase of the Brillouin zone. Sorry, decrease of the Brillouin zone.
So is it commensurate?
It's commensurate.
So like doubling.
It's just exactly that.
So have pressures above that? Does it stay linear at higher pressures, or does it just keep bending?
Up to the highest pressures we got, it's safe. But it would be interesting now to go to higher pressures, absolutely. Because we only did this in a piston cylinder cell, so we couldn't get that much higher. Yeah, but that's a good point.
So this is the BCS or not BCS?
It's probably BCS. There's a lot of work that, like in terms of the superconducting properties in this material class, a lot of work is done. Or many groups, like especially in China and Japan. From what I've seen, like the data could always be quite well explained or interpreted in terms of BCS, strong coupling theory.
Just reconcile the figure on the right and the one on the left.
Okay. You mean why? Because it says 27? Because this is low.
No, but where's the linear? The one on the left is calcium response.
Yeah. So basically, we start out here, and T star is high. It's like 150 Kelvin. We bring it down by pressure, but it doesn't go all the way down. It's not enough. So then we sort of replace some of the strontium by calcium, which is smaller.
Yeah.
So now T star starts at 80 Kelvin, and we can bring it down at 27 kilowatt to about 30 Kelvin. But it's still not all the way down. And there's actually a lot of other stuff going on which might be interesting, like why does rho zero go so much? Anyway, then next step, replace all the strontium by calcium. So now T star starts at 35 Kelvin. Now you can get it all the way down. That's basically what's going on. And it's only really convincingly linear when you get to this point. You could argue, well, isn't it also linear here? But then it's then you have the transition and all.
If you find magnetic field, so
It just suppress superconductivity, but we haven't really got good data to analyze the power law down here. But there's actually a problem there as well, which is fundamental issue in a lot of materials like that, is that applying a field also changes the normal state resistivity. It doesn't just unmask the normal state underneath the superconducting state, but it also changes, like basically if you apply a magnetic field to get rid of superconductivity here, you'll find the resistivity also changes up here. So it's not necessarily all that telling. It's not that high, but it's still like of the order of 7 Tesla. Maybe, I don't know, don't quote me on that, it might be higher than 7 Tesla, but it is significant. Yeah, so the idea we put forward back then when we published these results was, well, okay, so what's going on is there's a second order structural transition, which must mean that a particular optical phonon branch must get soft. This frequency goes to 0 at the transition temperature. And perhaps it doesn't just like deform and go soft only at this Q vector, the whole branch might come down. And so now we have low energy optical phonons. And if you work through the theory for scattering of electrons from phonons, can sort of contract a lot of integrals and so on, complicated looking formulae into a relatively straightforward sum over phonon Q vectors, where it's always the Bose occupation number of each Q vector which matters. And because that goes like 1 over e to the energy over temperature minus 1. If temperature becomes large compared to omega, right, then this expands out. You get basically just T linear resistivity. So that's effectively similar to the equipartition theorem. The degree to which these modes are activated, are excited, is proportional to temperature, provided that the temperature is large compared to the vibration frequencies. And if this mode really has come down to low frequencies, so then if one's temperature is like above this scale, then we should see a linear in temperature resistivity. And in fact, many metals have a linear in temperature resistivity once you get above about 80 Kelvin. So you need to get to some fraction, significant fraction of the Debye temperature, which is usually around room temperature, right? So Debye temperature divided by 3, let's see. So then you start to see a linear in temperature resistivity. It's not unusual at all. It's like happening in copper. But the funny thing is it's happening now to lower temperatures. So this temperature scale has been lowered. The idea as well is because we have a soft phonon block. But I was never really personally convinced that this can be the full story, because it's difficult for me to believe that the dispersion of this branch really stays small enough. Like the frequency will go to 0 around here, but it should still have some significant dispersion. So I always found that a bit unconvincing myself as a full explanation. So I'm beginning to wonder, and this is not, it's difficult to prove, but I think it's a promising idea that what happens if we also add in the fact that phonons have a finite lifetime. Normally, we don't have to consider that. Because if you think of acoustic phonons, for example, there are effectively conservation laws, if you like, or there are good reasons why the phonon scattering rate will become smaller and smaller when the wave vector becomes smaller and smaller. It's a bit like Fermi electric theory, where the lifetime sort of diverges as the quasi-particle energy approaches the Fermi energy. Likewise, here the phonon lifetime, I think, diverges if the wavelength goes to infinity for acoustic phonons, so they always remain well defined. And for optical phonons, well, they have very high frequency. So if you add in a bit of damping, they're still at high frequency. So, basically, they still have a high quality factor. The ratio of frequency over damping is high. So normally you don't consider it. But if you can now soften one of these branches so it goes to low frequencies, well, eventually the damping, which I think I've sort of sketched as like a shaded region here, well, that may become relevant. The quality factor may become of order 1. Or ultimately, what if they become overdamped, which would be this scenario? So what happens then? So if you think about the response function of a damped harmonic oscillator, this is really what it is. So it's something quite dramatic happens. So it has poles, it has zeros in the denominator, and for in the complex omega plane, like there's an imaginary part, a real part, and normally they sit near the real axis. But if you increase the damping, then the poles move on towards the imaginary axis. They hit eventually the imaginary axis. That's when they are critically damped. And then if you increase the damping further, one pole moves on to minus, so to imaginary infinity. So that's very rapid decay. The other one moves off towards 0. So that's very long-lived. So with very high damping, modes actually become very long-lived. The overdamped modes have a very slow relaxation rate. Relaxation rate goes as effectively omega squared over the damping. So damping becomes large. See, the spectral weight basically now is shifted from up here to down there. So now you can, in principle, exceed that relaxation rate at a much lower temperature, is what I'm saying. So in order to get effectively equipartition theorem response, the temperature would have to be here, right, for an underdamped oscillator, but it can be down here for an overdamped oscillator. So damping doesn't just broaden the response. The important point is it shifts it towards 0. And of course, this is not new. I mean, this has been, it's just, for me, it was new, like a few years ago when I first made the drawing. So it raises the question, which is an interesting possibility, is there actually evidence for this? It's not so easy to prove that you're dealing with overdamped phonons in a particular system, but and it's also a question which immediately arises if you're theoretically minded, like why would they be so strongly damped? What would dampen the phonons? They have to scatter from something, right? So they can scatter from each other, which basically means there's an anharmonic potential that they're moving. So if there's a strongly anharmonic potential, fourth order terms, that introduces phonon-phonon scattering. But then they have to, basically, that means two phonons can collide or a phonon can decay into other phonons. But those other phonons would have to have lower energy. So what if their spectrum has no lower energy phonons in it, how would that work? Or, and I think that's perhaps an interesting question to pursue, is it actually the electron phonon scattering itself which produces the damping? Because there will always be lower energy electron excitation that you can make. That's, well, I don't know what, yeah, the softening comes from the fact that we get in a structural transition. So that just means, almost by definition, that some phonon, some distortion mode has to go to low frequency. Question now, which I don't really see, is why would that be strongly damped? Simplest explanation could be impurities. Phonons will scatter from impurities.
So how that can see probably?
The softening, yes, but the damping, I don't know how you would see it. So far, I think it's been seen. So I certainly saw even old papers from the 70s in ferroelectrics and so on, where people did neutron scattering, and they could see the clear evidence for phonon damping and even insulating materials. Question is, can it be so strong that a low-lying phonon gets altogether overdamped? I'm not sure I've seen evidence for that, but maybe you will know. So let's turn to another material here, which is kind of similar bismuth. So similar, but also very different. Bismuth, of course, you may know as a semi-metal, very important material in the history of condensed matter physics, perhaps like the hydrogen condensed matter physics, thousands and thousands of studies, but mostly a long time ago. And it has a very low electron concentration, about one conduction electron in 100,000 atoms, and which made it easy in the early days to see quantum oscillations because the Fermi surface pockets are so small. Now, if you apply pressure, you can actually reduce the carrier concentration further. That's why we studied it in my group, because I just thought it would be interesting to see what happens. And it turns out you can effectively turn it from a semi-metal into a semiconductor. You can decrease the overlap between the conduction and valence band. Eventually, it will go to zero, which was motivated by the idea that you could reach the quantum limit in this. That's why we had a look. So you can use this logarithmic scale. You go from 1 microcentimeter here to 8,000 or 9,000 microcentimeters. So many orders of magnitude increase in the low temperature resistivity. But that's known, and it's kind of interesting, but we actually then focus on something else. Namely, at high pressure, the material undergoes a structural transition into a new phase, the Bismuth-II phase, and then a second structural transition into the Bismuth-III phase, which is the red line, resistivity versus temperature of Bismuth-III. So you go from, as a function of pressure, temperature, one semi-metal phase, which has been mostly studied. There's a slim sliver in the phase diagram of this Bismuth-II phase, and then a wide range Bismuth-III. And in the Bismuth-III phase, you have superconductivity at about 7 Kelvin. You have a high carrier concentration. And what was striking, you also have this very steep linear temperature dependence of the resistivity, like we just saw in this material with the structural phase transition.
Question? You should repeat for the online audience.
Only if it's good.
Okay. Many strange metals exhibit a very strongly temperature-dependent Hall constant with a T-squared Hall atom. What happens in the examples you've been giving us?
Okay, so this is a good question. I will repeat. So the question was, what is the temperature dependence of the Hall angle in Bismuth-III? Because in many materials, so strange metals, the temperature dependence of the resistivity may be linear, and the Hall angle is quadratic in temperature. And I have to admit, in this case, we haven't done it. We have measured the Hall angle. To my to apologize for this or justify my response, it is not so easy because you have to go to fairly high pressure. So it's not a zero pressure measurement, but we should still do it. I think it's a great suggestion. You have to convince somebody. Currently, all resources are somehow dedicated to other materials. So convince somebody that this should be interesting. But I agree. It's a really good idea. Because it's striking fact is that resistivity is linear in temperature, at least over some range, and also quite steep if you compare to lead, which is next door in the periodic table. So this is what resistivity of an elemental metal normally looks like. Right? And this is what you have in Bismuth-III. So Bismuth-III has a very curious structure. And that was discovered in Edinburgh about 25 years ago by the High Pressure Institute there. It has, of course, these are all bismuth atoms, but you can think of it as two interpenetrating sublattices. The gray atoms, right, they form tubes. If you look down like a cut of the material, you see a circle, and then along, perpendicular to the cut, you can see this extends into a tube. And the purple atoms, they form chains which line up inside the tubes. And the chains have a lattice constant which is incommensurate with that of the tubes, which is basically a marvel. But I don't, now it's just like, well, this was discovered 25 years ago, but I mean, why would something like that happen? So I'm still somewhat surprised that things like this are possible. And they're not just, it's not just bismuth. There are many elements which do this. Especially group 5 elements, like bismuth, of course, like antimony and phosphorus and arsenic, but also potassium and barium and scandium, and so there are quite a few.
There's no rational way.
Exactly, it's not a rational ratio. It's an incommensurate. It's called an incommensurate post-guest structure.
But is there, when you make a measurement, you have a finite number of significant figures.
Oh,
so
okay.
do you have some deep reason why, it's an irrational number that's rational, they are not?
How do you prove that it's precisely irrational?
It changes with temperature.
Okay.
The ratio changes with temperature.
Yeah, I guess ultimately you could just jump from one ratio to another. But yes, it's a difficult one.
But how to think about this? So this can just slide around. Or...
This is the point. Exactly, you guess. Yeah. So in this, again, these ideas, like the response function of a harmonic oscillator, they're not new ideas. They've been around. Was postulated in like 1938 by a Russian colleague that if you have incommensurate structures like this, then you should have no restoring force for one sliding with respect to the other. Right? So we have here effectively the the solid line shows the potential provided by the white circle atoms here, in which the dark circle atoms are sitting, because they are not in commensurate positions. They're not in commensurate positions with respect to that oscillatory potential. Their potential energy effectively always adds up to the same value, no matter where they sit. So the energy is independent of how you adjust, the relative positions of the two sublattices. So there is therefore no restoring force. So it's called the sliding mode or phason, that the sliding of the two sublattices with respect to each other. But it's also a bit like an optical mode, right? Because if you think of some unit cell, you can imagine that some atoms are moving to the right and the others are moving to the left. So it's not an acoustic mode. They're not all moving in the same direction. They're moving in opposite direction. So it's an internal degree of freedom. It's an optical mode.
Don't you have to worry about pinning?
Yes, absolutely. And, so the discussion of structures like this goes back to the mathematicians have been thinking about this since the 80s, and there's a so-called Aubrey transition, which is very interesting possibility that if the interaction between the black and the white atoms becomes quite strong, right? Then it may be favored for the black atoms to lock into commensurate positions and then allow defects, right? So you have a defect structure. Right? So because of course the number isn't right for the number of atoms isn't correct for having a commensurate structure, but you could have a commensurate for a bit, and then a defect, and then commensurate again, and then another defect. So there are all kinds of interesting phenomena in these materials that one might study.
You mentioned this early work on the one-dimensional chain compound, which I used to work on.
Is this the mercury one?
No, this would be like TTFTC and
Okay.
Krugman salts.
Okay.
These things they were trying to use this model to use sliding charge density waves for throwing. That was the original explanation of the 58 degree TC and TTFTC. And so people were really studying this, and it turned out exactly what Carney said, was you need one defect in it, and you get to see the oscillation rate.
So what I would imagine is
question.
Oh, should I repeat the question? Yes. So the question was, sorry about that. The question was, what is the role of defects here in pinning sliding mode? And I guess it would be interesting to study in this particular instance, but you would obviously, you would expect these sliding modes not to just slide on forever. Ultimately, the atoms would drip out of the end of the bismuth sample, right? So they have to be pinned, but that doesn't take away from the general idea that the phonon frequency will be lowered. Right? So it may not be lowered absolutely to zero, right? Right? There may be effectively a small gap, residual gap, is what I imagine would be happening. But again, it's like a whole area of investigation that I think is somewhat open. Like I found so many papers, theoretical papers on this area, right? But not many experimental investigations, which is basically these incommensurate structures were only really discovered 25 years ago in these elements. And most of the investigations on those elements are structural. Like, what is the precise arrangement of the atoms? Not what are the excitations? What is the excitation spectrum? Because that's quite hard. You have to do it at high pressure. Okay. Well, the other thing is also hard. I'm not taking away from that. But but to convince you, hopefully, that there is this phenomenon of lowering. Oh, more questions. Go on. Yeah.
Does the ratio of C gas to C most corresponds to any specific number? And does that happen here?
Yeah. So the question was, what is the ratio between the lattice constants between guest and host sublattices? And typically in bismuth and other elements like that, it's around 4 to 3. But it's actually not exactly, right? That's the point. It's like irrational. So it's like 1.31, but also not 1.31, more digits. And I guess ultimately somebody must come along and explain why is a material stable? Like, why is this the favorite structure and not the standard bismuth structure? Right? So at the moment, I'm just sort of saying, well, these structures exist. And if they exist, they must have low energy excitations. Right? And that may explain why we're getting linear and temperature resistivity. Then you ask, well, why on earth would it be stable? Right? And that has all been, like, people are looking at that in particular, things Graham Ackland in Edinburgh and others, are making up, like, their ideas about trying to gap out as much as possible of the Fermi surface, or maybe more microscopic picture. I don't know. It's a tricky one. Of course, just to say one more thing, there's a relative to invariant, a structure like this forms, and it can transform into a commensurate structure, which has 768 atoms per unit cell. Right? Then, why does it have 768? Why not 772? Right? So, I just find it all wonderful.
Two questions. One question and one observation. The question is, are all these examples metals or are there insulators that way? They're all metals.
So the question was, are these all metals? As far as I know, yes.
Okay, thank you.
As far as I know. Or maybe not. But it's superconductor.
And also, there are, of course, similar phenomena in magnetism where you have commensurate and incommensurate transitions in magnets and incommensurate phases whose Q vector evolves continuously. So is there parallels with that, or is it completely?
I don't want, maybe I'm getting more and more drawn into an area. I'm not, so the question is it related to phenomena in magnetism? And ultimately, of course, so there are incommensurate structures in magnetism. They would presumably have similar sliding excitations, right? What is, and just like sliding charge density waves. Right? This is another phenomenon like that. And there's, again, a whole community working on these things. And I've been to a couple of their conferences, in fact, and it's very interesting. But one thing that is special about this is it's not, if you like, a commensurate structure which then is host to a modulation. Right? The modulation could be incommensurate, which is the case in magnetism or with charge density waves. Here, the structure itself hasn't got a unit cell, right? So, so it's actually, that's, I think, what is special here is that the phason mode is actually built in. Like, you have a low end, like in the structural transition material I showed earlier, you have a low frequency phonon, but you have to fine tune to it. And then you can generate it. But it's not intrinsically in the structure. Here, it is built into the structure. Okay, so the idea here was Bartomeu at the time, Montserrat, he did phonon calculations of using approximates, because you can't do it for the full incommensurate structure that would have infinitely many atoms per unit cell. So here he has 42 atoms per unit cell, so you have lots and lots of optical modes. And what you find is that, in fact, 2 come down in frequency and become solid. Right? So this is even now for a commensurate, because it's a approximate structure. So it has a commensurate structure, but a large unit cell. And so you can convince yourself then by calculating the lambda for electron-phonon coupling for such a phonon spectrum that it is actually significantly enhanced by these low-lying optical modes. So just to emphasize again the point I was trying to make, if you look at electron-phonon scattering in this way, that is basically comes out of calculating the variance, of the displacement of the atoms. There's a trick, you have to take the temperature derivative, multiply by temperature again, but that basically doesn't change much. So, and then the variance of the displacement you can get from the response function via the fluctuation dissipation. And now if you look at the response function of a damped harmonic oscillator, and I plotted it as imaginary part over frequency, you notice it has this tail. That's the important thing. So it extends to zero frequency. Pi double prime over omega is constant at low frequency. All right. So if I now stick that into this formula to get x squared average, then I have in my formula omega, because pi double prime is proportional to omega at low frequency, omega times n omega, the omega. And you can just do a substitution here to see, that because this has this form, omega over temperature, that you just see by power counting, this must be proportional to t squared. So you immediately get that for electron-phonon scattering, as soon as phonon damping becomes relevant, the low temperature resistivity should be proportional to t squared. But we don't see linear NT. So linear NT, okay, we would get if the scattering actually, if the phonon become overdamped, which is what I explained earlier, so that your temperature scale doesn't lie, like I said before, it would lie like in the tail here of an underdamped response, but it lies above the peak of an overdamped response. And then you would get linear NT. But question is, would that even persist as the temperature now approaches T equals 0? Well, that now depends on details. So there'll be, what I'm just saying is the cutoff, or the changeover from linear NT to T squared resistivity, right, happens when the temperature reaches here. So below we would see T squared because basically pi double prime over omega becomes constant, just like it was for the underdamped response. But also what this does not yet take into account is that the response function itself will be different in different Q vectors. So there may be a question of dynamic exponents that you have to look into the details of the theory. Okay, I'm not making great progress.
Yeah,
but I think you predicted that.
Do watch your time, because although we have a lot of questions,
you will keep me up.
We will stop at 1:20. At 11:20.
All right. I'm already feeling rather weak. So I'm not sure I could go on until 1:20. Anyway, so maybe I'll speak faster. That's probably the answer. So the next topic I want to get to is question of mass renormalization. So in so heavy semi-liquids, and this is a long-running project on nickel disulfide, the Mott insulator. Generations of students that basically work on this. Hui Zhang really was one of the key drivers early on. Sven Friedemann, now in Bristol, was super important. Who some of the crystals did high pressure experiments, high field experiments. Then Konstantin Semeniuk is now in Dresden, and Pascal Reis who's in Stuttgart, and Jordan, who is in Schiphol. And of course, a lot of these measurements were done at high field facilities. And maybe you know actually quite a few of the people on there. I should particularly highlight, I've almost forgotten, Patricia Alireza, who's with us in Cambridge, and she's behind all our high pressure efforts. She's basically training all the students setting up the diamond anvil cells. And so she's not always involved in the actual experiment, but she's always behind every experiment. Okay, so this was data taken by Sven when he was working in Cambridge, and on nickel disulfide. Nickel disulfide is insulating at zero pressure. Resistivity versus temperature turns up here at low temperatures, but as you increase pressure, you don't need much pressure to turn it into tap. it's about 30 kilobars. The insulator to metal transition is at about 3 gigapascal, which is 30 kilobar. And what was really important, and that basically motivated this work, was that we could see that the residual resistivity is as low as about 1 micron centimeter. So you can make ultra clean nickel disulfide crystals, single crystals using tellurium flux, which are pure enough that you should be able to see quantum oscillations. But it's a tricky experiment to search for quantum oscillations under pressure, because you need to put your sample inside one of these tricky anvil cells, and the samples are tiny, 0.1 millimeter, maybe 0.2 millimeters. The way we do it is put a little pickup coil around the sample and make that part of a resonance circuit, an LC resonance circuit. And then we measure the resonance frequency of that circuit. So that's we call it TDO because it sounds rather technical, because the so-called tunnel diode is used to drive the resonance. But that's sort of that's kind of technically very important, but conceptually unimportant. Point is, we measure the resonance frequency of an LC circuit, and that depends on the properties of the sample. In particular, it depends strongly on the resistance of the sample via the skin depth phenomenon that happens at high frequencies on such metallic samples. So you can deduce from changes in the frequency, you can deduce changes in the skin depth, which give you changes in the resistivity. And frequencies you can measure very accurately, a few hertz per 100 megahertz, so basically 1 in 10 to the 8 resolution, which you cannot get easily using straightforward 4-point resistivity measures. So it's actually quite a nice technique. It has a lot of pitfalls, but for seeing oscillations, it's very nice. It's ultra high resolution. So this was a measurement on nickel disulfide at 50 kilobar in a metallic state. And you see beautiful quantum oscillations at 20 Tesla, but going all the way down to less than 8 Tesla, like clearly there at like 7.6 Tesla. So first time perhaps that in a transition metal Mott insulator, you could see the signature of the Fermi surface in the metallized sort of Mott metal state, which is highly correlated. And you can measure the mass of the quasi particles by looking at the temperature dependence of these oscillations, of the amplitude of these oscillations. The mass is enhanced. It's not super high. It's like 4 electron masses. But the band mass from BFT calculations would be about 0.7 masses. So it's already 6 times enhanced over the band mass. And you can look at the angle dependence of the frequencies of these oscillations. Because the oscillation frequency tells you the cross-sectional area of the Fermi surface. That angle dependence gives you a way to figure out the shape of the Fermi surface. And it turns out to look like a little cube, which takes about 1/3 of the volume of the Brillouin zone, from what I remember. And it basically consists with exactly what you would get from a DFT band structure calculation. Now you might say, why does band structure calculation give me metal at all? Because this is an insulator. But the point is, it's only an insulator because of strong interactions, and they're not apparent in the band structure calculation. So band structure calculation actually gives me the metallic state, which I need pressure to induce. Now, when you track these oscillations as a function of pressure, we went from about 35 kilobar, which is roughly where it first becomes metallic, all the way to about 100 kilobar. And you can see the frequency of oscillations and also the mass. So the frequency doesn't change very much. It's almost constant. It just changes a little, which is exactly what you would expect when you compress a solid, because the atoms come closer together. So the Brillouin zone expands and the Fermi surface expands with it. It's actually almost exactly that effect. But the carrier mass changes quite a lot. It's near the insulator transition, it's about 6, and then it goes down to what, about 1.5 at 100 kilobars. So there's a strong pressure dependence. And then we also checked like what happens to the mean free path and so on. And it's roughly constant basically once you're in the metallic state. Now, the reason I want to flag this up was because there's another phenomenon in nickel disulfide, which I didn't really talk about much before. It's also magnetic. It's a magnet at ambient pressure, but also it's known to be magnetic in the metallic state. And that magnetic transition, antiferromagnetic transition in the metallic state goes away at about 70 kilobar. So there's a quantum critical point at 70 kilobar. And in fact, in Cambridge, this was your PhD. So Philip worked on this. Yes, there's a question like, because there wasn't religion, obviously, Gill would have said, wow, well, shouldn't there be superconductivity? There's a quantum critical point, and he persuaded, I think, Philip? Yeah, you don't maybe to talk about it, it's fine. But anyway, people not just there, but elsewhere were looking for the superconductivity. And so it's because there's a quantum critical point at about 70 kilobar. Maybe we should look again. But the point I'm making is there's no obvious signature in the mass at 70 kilobar. I mean, there may be, we don't have that much resolution. These are really tricky measurements. There may be a little bump, but the overwhelming effect here is this rise. So to me, it's like, okay, so I regard the band mass as arising fundamentally from the local interactions, which is the Coulomb repulsion in the Mott insulator. Right? And that provides the baseline band mass, the narrow bands. On top of that, you then have correlations in long-range interactions. They will induce magnetic transitions. They will induce corrections and really interesting things like superconductivity. But on a scale like this experiment, you may not even see that. And here's another example of this idea when we worked on yttrium and 2 germanium-2 quite a lot in my group. We should be a bit more respectful to all the people who did the work. So again, over the years, a lot of PhD students have worked on this. In particular, the main breakthrough came when Chen, still in Cambridge now, but maybe not much longer, was able to produce really high quality crystals, resistance ratios of 700. And this shows Alex McCollum, Rosalind, doing high field measurements on it in Nijmegen. But most of the Fermi surface studies actually were done by Jordan and PhD student Karen here in Cambridge. So, point with yttrium iron to germanium-2 is it's one of the few iron-based superconductors that don't have a nictide or chalcogenide element to make up the structure. It's a German. And it has a fairly low TC of about 2 Kelvin in resistivity, 1.2 Kelvin in heat capacity. And it has a very high Sommerfeld ratio, about 100 millijoules per mole Kelvin squared. So after we were able to make good crystals, 700, the question was, okay, can we map out the Fermi surface? Fermi surface looks quite different from other iron-based superconductors. Most iron-based superconductors are highly layered, very two-dimensional. So the Fermi surface is made from cylinders. Here, DFT calculations sort of say, well, it's very three-dimensional. You have these sort of ellipsoidal pockets, one small one larger one, then a big one here, which looks almost like a pillow. And then you have electron pockets on the corner, which may have these noses sticking out towards the center. And the DFT calculations also say, well, we should expect about 70 millijoules per mole Kelvin squared heat capacity, but what we measure is 100. So there's a 6 times mass enhancement we need to understand. Again, this was done in the Cambridge cryomagnet, beautiful quantum oscillations using mutual inductance setup, DHVA. And I don't want to get too much into the technique, but there's a beautiful rotator system there. So you can take the samples, see how the oscillation peaks, so the power spectrum change with rotation angle, and you can track here 3 frequencies, and they could be assigned to the alpha, beta, and gamma surfaces, 3 of the 4 surfaces. The 4th one we only picked out by doing measurements in Nijmegen. So the point was that all of these follow quite closely what you would expect from DFT calculations. So the dotted lines are the DFT results just from the picture I showed in the beginning. So and then the dots are the measured data. So basically, we're fine. You may even ask, well, why did you bother with this stupid experiment? Like, you spent so much money on liquid helium to measure this, and then we just see what we could have got from a few hours of computer time. But the point is that the experiment doesn't tell us the mass correctly, right? So sorry, the calculation tells us 17 millijoules, and we need to get to 100. So, so looking at the mass measured on these three Fermi surface pockets by basically doing measurements at different temperatures, you can find that the mass determined at different angles and so on, these are the dots, it actually tracks very well, the experimental measurements track very well the DFT results, the computational results, if you multiply up the computational results by a factor of 5. Okay, so the computation gets it wrong, but it gets it wrong by the same factor every time, every direction, every sheet that we could measure. So it's uniform mass renormalization. And that, at least in first order approximation, you can say, well, that means, well, mass, everywhere on the Fermi surface, the mass has been changed by the same factor. It's not a quantum critical phenomenon where you may have had, like, regions of the Fermi surface, hot regions are connected by critical wave vectors associated with fluctuations, and you get a mass renormalization there, and they stay unrenormalized elsewhere. It's the same everywhere. So this measurement suggests that there's a local mechanism driving the mass renormalization. There'll be, of course, more, right? Because it's close to the border of magnetism, there's superconductivity. There'll be more phenomena, but the underpinning, the baseline mass renormalization is presumably local because it happens similarly in all directions on all parts of the Fermi surface. So this is what I'm trying to get across. Yeah. So my picture here is that we start out with a weakly interacting system which has broad bands, like the blue one. We then have a local mechanism like phonon repulsion, lithium-ion to germanium to maybe Hund's rule coupling, could be in iron-based superconductors that you would say is a Hund's metal. Basically, the tendency of the several electrons which sit on each iron side to align their spins. They're basically forced to align their spins locally. So when they want to hop, it's hard because they have to hop onto a place where the spins are also aligned in the same way already. So it basically impedes the motion of the electrons, slows them down, gives them a smaller Fermi velocity. Right? So we get narrow bands. On those narrow bands, you can then have likewise slow fluctuations, charge fluctuations, and spin fluctuations. So you go from broad fluctuation spectrum to a narrow fluctuation spectrum because you have narrow bands now. On top of that, you are close to the threshold of magnetism usually, so you get an exchange interaction between neighbors, which will drive instability. So at an instability, this fluctuation rate, which is already low, can go towards zero, can become even smaller. And it introduces dispersion into the picture, and the dispersion means effectively if something is strongly dispersive in Q space, it means it is it gives long range in real space. So you can get longer range and long-lived correlations, which can provide a pairing interaction and then superconductivity.
So the stamping is a spin fluctuation?
Yes, it's the spin fluctuation rate. Yeah.
Different from the previous one we talked about.
Yes.
Phonon.
Yes, I'm more. I think I wanted to introduce the phonons because I think it's a less known concept there, and I find it intriguing, but it's also simpler to understand because it's just mechanical, because you're just thinking about what normal modes of vibrations being there. Okay, right, let's turn to
20 minutes.
20 minutes should be fun. So the CeSb and UTe2 project, and thereby the question, why do heavy fermions often have quite high critical fields? And I think, I don't know, of course, but I just want to raise it as a question. So again, the project which goes back quite a few years, we basically first grew CeSb and UTe2 when I was keen to develop crystal growth in the group, and it was known to be one of the simplest materials to grow using flux growth. So it was more like, oh, let's try this one. And then it turned out to be really interesting material. And so the draw came actually to us from Raw always. So he was with me like in 2007. So I think he grew this like in 2010. So and then Philip has worked on this because we did high pressure X-ray diffraction. So and then more recently, for Theo, who is here, and Zhisheng also were key people, Stephen, Christian, and Oliver. They've all left by now, and they finished their PhDs. Okay, so the story about cerium antimony 2 is that at ambient pressure, it has a remnant magnetization. It looks like a ferromagnet. It's actually more complicated. It has several consecutive magnetic phase transitions. But it looked like an interesting candidate for investigating a ferromagnetic cerium-based heavy fermion material, because there are not so many of those. And there's been a lot of work by the Ames group, so Paul Canfield and Sergei Budko on this material prior to our work. So here's what you see when you measure resistivity versus temperature at different pressures and low pressures. Well, you know, resistivity decreases. There's an anomaly here. When you look closely, there are actually 3 anomalies which correspond to the 3 magnetic phase transitions. And what we wanted to see how they would go continuously to 0. So we have a quantum critical point. But this doesn't happen. They don't actually change much with pressure. Instead, at 21 kilobar, the resistivity curve just changes completely its appearance. And now there's a kink in the resistivity at much lower temperatures, about 3 Kelvin. So when you fill in the gap, what you find is that this is the low pressure curve, and then that's the high pressure curve. And in between, there's a range where the resistivity jumps from effectively the higher pressure to the lower pressure curve, like here. And these are hysteretic. So a bit more thought reveals, well, this material is actually changing its structure. You see? So it's got an ambient pressure structure, and it's got quite a different high pressure structure. And if you're cooling through that transition line as a function of temperature, you see that structural transition as you're cooling. So there's been quite a bit of work on resolving the high pressure structure. I mean, you know what it is. It goes basically to the structure that is also adopted by terbium antimony 2. So there are several possible structures for the lanthanide diantimonides. And we just tried to match X-ray diffraction results, which as a function of pressure, against different candidate structures, and the high pressure structure matches this one best. It also is what Theo's calculations suggest, actually, that it should be the same one. Now, let's focus on the high pressure structure, because that turns out to be the really interesting. You do mu-SR relaxation measurements, which was done at PSI under pressure with Wust and Prasanov. You find that on cooling, you get a signature of magnetic order, which are these wheels, and the data basically have a change in decay. And so you can see, oh, all right, so at 70 kilobar, there's this onset of magnetic order, and that onset shifts to lower temperatures and higher pressures. We think it's an incommensurate spin density wave order. So this is now the situation. So we have a structural transition, the red line comes down as a function of pressure. You can cross it in X-ray diffraction at high temperatures, and you see the transition here, or you can cross it at constant pressure as a function of temperature, and then you see these jumps in the resistivity that we saw. And then at high pressure, you have a magnetic transition. And this magnetic transition extrapolates to 0 somewhere. And that should be a quantum critical point. So that's where we should look. This is basically how like 90% of the research in my group works. So, oh, okay. So there's a phase diagram. Here's an interesting region. Let's have a look. And it was a little tricky because it's just outside the range, on the limit of the range of this cylinder cells. So Oliver Spire, who did these early measurements here, used an angle cell. And what you find is, first of all, you can see this kink in the resistivity. Still, the residue is the magnetic transition. At 28 kilobar, at 32 kilobar, it's gone. And at low temperatures, cerium antimony 2 goes superconductor. So we found one more of these cerium-based high pressure superconductors. And it's quite convincing because you can also see the susceptibility. It's a kind of an interesting material because everything happens at such low temperatures. It has, in the lingo, a very low Kondo temperature. If you look at resistance versus temperature on the big scale, you can see at like 30 odd kilobar, the resistivity is basically flat from room temperature down to like 10 Kelvin, and then it collapses. Basically, most of the change is actually below 2 Kelvin. This is just going from 0 to 1. can already see we're up at 40 micron centimeters, which is about a third of the full resistivity. So everything is a very low temperature material. And it has, like many of these materials, a linear in temperature resistivity at the critical pressure. So here's the phase diagram, deduced from resistivity, but also heat capacity measurements. And basically, this is a magnetic transition, which comes down. Then there's a superconducting dome around 30 kilowatts. There's probably another magnetic transition. We haven't yet figured out what that is. But there are two anomalies in the heat capacity. So looking just at that critical pressure, resistivity is linear at very low temperatures, and then it curves over because eventually it saturates. What caught my eye particularly was that the critical field is quite high. So this is the upper critical field of theorem Antony 2 versus temperature. We start out at about 220 millikelvin, and the critical field, by now it's actually been measured in dilution fridge to higher, down to lower temperatures. So this dotted line is actually confirmed, but the critical field is of order 4 Tesla. So, which seems high if you consider that the transition temperature is only 200 millikelvin. Because there's a limit of the transition temperature field, the Pauli limit, which sort of says, well, about twice the transition temperature in Tesla is what you would expect to be the limiting field. So it should be 0.4 Tesla. Said it's 4. There's also this strange shape of the curve here, this S shape, which is kind of surprising. We think it may just be explained by the fact that we are just inside the antiferromagnetically ordered part of the phase diagram. And when you apply a field, you're not just suppressing superconductivity, you're also affecting the magnetic order. Because this S shape goes away when you have higher pressure, when the interferomagnetic order is gone. Okay, so I only have 10 minutes left. Maybe I should skip the theory part. I was hoping to explain orbital limiting, but let's just look at the Pauli limiting. So the important thing with Pauli limiting is if you have a singlet superconductor, there's a limit to the field at which it can sustain the singlet state, because it's advantageous for the singlet to break up so that you can exploit the full Pauli susceptibility of the material. This free energy contribution in field in the normal metal would involve the Pauli susceptibility. But if the susceptibility is basically zero because the spins are bound into pairs of singlets, well, then you lose that. But you gain the condensation energy because you're not superconducting. So there's a crossover between the two curves, either superconductor, no field dependence, but you start out with a lower level of the energy, or metal, and then you gain by letting the spins flip. So there's a crossover, and that's the Pauli, that's the Pauli limit field. And that's usually basically proportional to TC. But when you look closely, it's not that easy because it's only independent of the density of states, which comes up in both of these, because both densities of states are usually taken to be equal, but then fundamentally not equal. One is the density of states that dictates superconducting properties, and the other one is the one that dictates magnetic properties. And there's a relatively subtle argument for saying, maybe if you ask the questions, I can return to later, but for saying that the magnetic susceptibility really doesn't see the full quasi-particle susceptibility, the full quasi-particle density of states, which in a phonon-mediated superconductor always peak at the Fermi energy. It sees the underlying band density of states. So the two susceptibilities may differ by a factor of 1 plus lambda. And there's another issue that in the Pauli limit calculation, the relation between the gap and TC plays a role, and that ratio is 1.76 in normal BCS theory, but it can be much higher in strong coupling. So when you take those two aspects together and you do a strong coupling calculation, the phonon-mediated superconductor, you find that the Pauli limit is actually much higher than one would think. It's not, let's say, 1.5 times TC. It's 1.5 times 1 plus lambda times TC. This was found in the 1980s by Schwarzman and Cabot. The number of papers on that topic look pretty convincing So, well, of course, in phonon-mediated superconductors, lambda is of order 1, so this is not a huge factor. But
Yeah, that's what 8 minutes took.
oh, innate, I thought you said 5. Okay, I was worried for you. Okay, so so that's usually not so big, but heavy fermion superconductors have mass enhancement in the factor of 100 or so. So then you see, okay, well, this could be much more complicated than it appears.
So if you want to have questions.
No, I don't want any questions. No, but seriously, if you have questions, go fire away.
So, Malte, you believe this is a singlet superconductor, because many people say as soon as you're violating the Pauli limit, or we have a possibility for something more exotic. Why are you so convinced it's a singlet?
No, I think maybe it's so the question is, why do I insist that this is a singlet superconductor? And the answer is, I don't. I'd love it to be a triplet superconductor. I think it would be great. But also, like let's just see what is the situation. So a lot of heavy fermion superconductors, and just quickly, we have always the Pauli limit calculated by the standard rule of thumb, and that's the actual upper critical field. And a lot of cerium-based superconductors, and even to the side the uranium-based ones, which are always a little bit suspicious, but a lot of the cerium-based ones break the Pauli limit by a long way. And so we jump to the conclusion, well, there must obviously be triplet, but is that really warranted, right? Because elementary calculations, not so elementary, but advanced calculations on conventional superconductors suggest the Pauli limit is perhaps much more subtle, right, than just this rule of thumb. So before we jump to the conclusions of triplet superconductor, let's just see whether we can understand Pauli limit for singlet superconductor.
Your argument was that the density states with the susceptibility wasn't enhanced. So does that mean the Wilson ratio is also different, the ratio of gamma to
That's true.
susceptibility? So you wouldn't get a proper Wilson ratio.
I think that's an interesting question. So for the question was, what happens to the ratio of susceptibility over heat capacity when you have electron-phonon coupling included? And indeed, it looks like it shouldn't be.
So that's an easy way to check.
That would be how we would check it.
But is this just one long devil's advocacy? I mean, why the heck are you even talking about electron phonon in these heavy fermion systems?
Because there is no, well, there are actually some calculations now for spin fluctuation mediated superconductors, U-wave superconductors, and they're actually referenced in our paper on this topic. But I think the most convincing calculations, the most detailed calculations, have been done in electron phonon. So because how would you do the calculation for for full cerium-based heavy fermion superconductor is beyond me, but I can look at the literature and I can see, well, clearly Pauli limit is actually quite tricky in the case of strong coupling. So now I want to motivate people like you here, or to have a go at checking this in a heavy fermion superconductor. I think that would be good.
So if I could get to the material that you haven't got to, uranium deuterium, that goes through the Pauli limit. So do you believe that's also similar?
So the question is UTe2 a singlet? Now,
Well, it's not in your chart.
exactly. But it could easily be, right? I'm not saying that all of these are necessarily singlet superconductors. All I'm saying is it's quite common for heavy fermion superconductors to break through the Pauli limit. Now, I think in UTe2 there's a lot of very convincing evidence from NMR that it's actually triplet superconductor. So I suspect that really is a triplet superconductor, but it's kind of a long. Whether the cerium-based ones are triplet is less convinced. So that's basically the point I'm making, and I think just like the question of overdamped, underdamped phonons is an interesting question I want to raise. I'm not trying to persuade you that uranium compounds are singlets. I'm saying actually Pauli limiting maybe deserves a closer look. And by the way, this is a calculation done on magnesium diboride, which shows like how this actually happens. That if you apply higher field to a conventional strong coupled superconductor, you have increasing admixture of an odd frequency spin triplet state. So in a way, they are actually triplets, you see. Because what happens is that the actual superconducting gap function is a superposition of even frequency singlet and odd frequency triplet. And in high field, the odd frequency triplet is increasingly favored. This isn't my work, of course. This was done 10 years ago by Oppenheimer group in maybe Lund, I think, in Sweden. So perhaps I don't think so. I think it was important. We're using the all right.
I'm sorry, but
It's
you're not gonna get.
That's okay. What I can do is that's actually very good because we have in the audience Tony, who at the back, and he's going to talk about UTe2 this afternoon. I think the main point there I was going to make is just like through a series of very beautiful high field measurements. Tony and Alex and other colleagues from the group have mapped out the magnetic phase diagram for UTe2, which shows how, in low fields you have SC1, the higher fields superconducting state 2, and then you have a very high fields, the superconducting state 3, which sits sort of, if you like, above the metamagnetic ceiling. You imagine the ceiling of this room being like a boundary in magnetic field space. So this is like one field axis. And then there's another one there and another one there, right? So the ceiling limits like a low spin polarization from a high spin polarization state. And it's above that ceiling. But I think Tony will go into the details this afternoon. Okay, thank you very much.
We have time for maybe one question, because we had a lot of questions during the talk and we need to keep the schedule. So we can ask that nice question. Go, yeah, yes.
So if you go back to, I think it was your germanium compound, and you said it's local physics, because the mass renormalization was uniform. What is the local physics that you were referring to?
I think it's not actually motivated by one of your papers with Andre Nevidomsky, Hund's metals, right? So, but it's but I don't know whether I get it back together, but they're like the basic idea is you have about 6 electrons per iron side. It's not like Hubbard model where you have 1 electron or something. Even the uranium compounds, you have 6 electrons. But there's strong Hund's rule coupling, which pretty much constrains the electron spins to point the same way. But it's not magnetically ordered. So there's some atoms that point up and other atoms that point down. So now for electrons, they don't move freely. Like this introduces a strong correlation because they can only hop onto another side if the electrons there are pointing their way. Broadly speaking, this causes the bands to narrow. I think in the language of Pierce's paper, it was much more intriguing because it basically made a link with heavy fermion physics. That if you have multi-electron system, the conduit scale is strongly reduced from so the bare conduit scale, like say of an iron compound, would be very high. But if you include the Hund's rule coupling, it effectively reduces the quantum energy. So that's equivalent to saying we have now something like a heavy fermion material, but it's not super heavy, but still 100 millijoules per mole Kelvin squared. This medium heavy. Oh.
I'm not going to comment on it. It's not my system. I thought we were talking about optical phonons.
No. This is completely different. This is the iron-based. This is Hund's metal physics. It's an iron-based superconductor.
Oh, okay. And that's okay. Well, let's thank Malte again. We've had